In this video, we will show how to use the Mathematica package xTerior to do more advanced computations with differential forms. xTerior is a package of a larger package called xAct. xAct is a very complete Mathematica package for doing calculations in differential geometry. It is maintained by hundreds and tested by hundreds of researchers, and it has a long history and a very good reputation. So xTerior is a sub-package of xAct, and in order to use it, the first thing you have to do is to install xAct, and you will find xTerior included in the installation. So you should visit the page of xAct and download the appropriate tarball for Linux or zip-archive for Windows, and there's also for a Mac. And installation is very easy because all you have to do is to unfold this tarball of files in the correct place. This place is different for different installations. You have to figure out which one applies in your case. Basically, you have to find where is Mathematica installed in your system and find the application subdirectory, and same thing also here for Windows. xTerior has its own web page, as it can be seen here. From there you can download its main documentation file. It is a notebook which you can open with Mathematica, but after you complete the installation, this file together with another nice to look at file here will be available in your local system, and you can open it locally without using the internet. So you have to figure out where they are. These are examples that will help you in your search. And then if you open those notebooks with Mathematica, you will see this for the main documentation of xAct. It is has a simple structure here to read in chapters, which you can has the description of every available function, some simple examples. And a more pedagogical introduction is to look at those slides here and learn more about also the full xAct project and how xterm is part of it, and examples of sessions like the ones that we will show today, but also even more advanced ones. So let's start the session. To start the session, we have first to load the package. It is a good idea, before you load the package, if you have already started Mathematica, to use the quit function to quit the kernel. xAct defines a lot of symbols under the hood, and you don't want to have any conflicts between your definitions and the xAct definitions. So if you start Mathematica from a fresh start, then evaluate this cell. Take some time to load. It's a large package. If everything is fine, you will see all those messages. You see that several other packages are loaded. It is instructive to read all the messages, but we won't spend time doing so in this video. And then we can start the session, and we will start with by doing simple computations with abstract differential forms. So the first thing we have to do is to define a manifold. In this case, where we don't want to specify its dimensions or a chart and do just general calculations with differential forms, we can use a manifold that has a symbolic dimension, and we use DIM as the symbol for it, which is not given any particular value. But DIM has to be declared as a constant symbol, and be careful with when doing calculations with xTerior and with xAct in general. If you have symbols that you want them to be treated as constants, you have to declare them, otherwise they will not be treated as constants. In this function also you see an option print as, and we will see this option several times, and it instructs the exact system to how to print this symbol in the output expressions. So this can be used to make the output expressions more legible than the symbols that we use in our input expressions. Then we declare a manifold by using the function defManifold. The first argument here, m, is the name of the manifold. So we use m as the name of the manifold that has dimensions DIM, unspecified, and then we put a list of the indices that refer to geometric objects defined on this manifold. So the choice here can be anything you like, and the list can be as long as you like. So we have to evaluate this cell to make the definitions. Then we have to define differential forms in order to use them. All differential forms must be declared using the function def_diff_form. In this function, in this simple usage that we show here, the first argument is the name of the differential form. So the differential form, you see, comes with its name, f, sigma, lambda, omega, but then we put empty square brackets. Mathematica works with geometric objects as being heads to expressions. So let me pause a little bit and remind you this concept, because it is very fundamental in Mathematica, and if you don't know what it is, you have to read the documentation and figure out what it is. So in Mathematica, everything is an expression, and every expression has a head. So when you add two numbers, you have an expression whose head is plus, or if you have a list, that is an expression that has as head the name list. So if you go to the documentation here, if you choose Wolfram documentation, and here in the search bar you put head, you'll end up in this page, and there are tutorials explaining here what is a head and how they can also be manipulated so that we can do useful calculations with Mathematica. So knowing that every expression in Mathematica has a head, and what is this head, or how you can figure out what this head is, gives us power into doing computations more efficiently. But here it is fundamental, because all geometric objects are defined as heads and not as symbols. So you see, this is a head that contains nothing here. So we evaluate this cell here. We see that it defines the symbols here to be tensors of the appropriate type. Then the simplest operation that can be applied on differential forms is the wedge product. So you can easily add the wedge product in your expression by using the wedge character. The wedge character is typeset by pressing escape. The carré, which on my keyboard is above 6, it's shift 6, but you may have a different keyboard in your case, and then escape again. So let me show you how this is done. So I press escape. I see this sandwich-like looking character. Then I put the carré here, and then I press escape again. A more verbose way into doing the same thing is to type a backslash, a square bracket, write the name of the character capitalized, and then closing the square bracket will make the wedge character to appear. So here, let's see how the wedge product of a 0 form f and a 1 form is computed. So you see the output here is simpler than the input. The square brackets have been removed, and the print as option is used to print those forms any way we like. Furthermore, the very simple rule that wedge product with a 0 form is ordinary product is also applied here. But this is not true in more complicated expressions. So if you want to apply the wedge product on two forms that are their type is higher than 1, so lambda here has been defined to be a 2 form, sigma has been defined to be a 1 form, then you see the result is lambda times sigma plus sigma times lambda, but the graded anti-commutative property of the wedge product is not used to simplify the expression. If you want the property of the wedge product to be used and simplify your expression, you should apply the function to canonical. To canonical is a very useful and heavily used function in the whole xAct ecosystem, and it is used to put tensorial expressions into what is called canonical form. So we'll see more about that later when we will use the xAct package more. So, but in this simple case, it means to put lambda and sigma in the correct order by applying the properties of the wedge product, and that will show us that the wedge product is commutative in this case. Of course, this is not true when we compute the product of any two forms, and now that we multiply a 1 form with a 3 form, the wedge product is anti-commutative, and by using two canonical we obtain this result. The most interesting operation on differential forms is taking their exterior derivative, and the symbol for this operation in exterior is DIF, F capitalized. So when X is an expression containing differential forms and we apply diff on it, then this is exterior differentiated. Here is a simple example. We have the product, sigma is a 1 form, omega, lambda is a 2 form, and you see the sign is computed correctly, the graded Leibniz rule is applied, and we obtain this result. Now, let's differentiate a more complicated expression. So here we differentiate a form that is obtained by multiplying the 0 form f with sigma, the d of lambda, and the d of omega. So when this form is differentiated, we obtain two terms where D is acting on F and sigma. Of course, when it acts on the other factors of the product, it gives 0 because D square of anything gives 0. That is why we only have two terms here. And we see that the first term here gives the action of D on sigma, and the second term gives the action of D on F. So let's make now more concrete computations by considering a manifold of specific dimensions. Let's take a three-dimensional manifold. We call it M3. Alpha, beta, gamma, delta are the indices used for geometric objects on this three-dimensional manifold. And we also define a coordinate system, a chart on this manifold. We give it a name. We call it Cartesian. That is what this first argument in depth chart signifies. Then M3 refers to the name of the manifold that we have just defined. 1, 2, 3 are the values of the indices taken by geometric objects on this manifold. And then we have the names of the coordinate functions. You see, the coordinate functions must be zero forms, so these square brackets here are mandatory. So these show that in its internal form x, y, and z are expressions that have heads with those names. So after doing this, you see a lot of work is done under the hood. A lot of things that we will not use are defined. So you can read those messages and get a glimpse of what is coming when we will learn to use xAct in more detail later. And now let's use this definition to write a simple expression that has the coordinate 1 forms of in this chart. So this is dx, dy, and dz, and these are obtained by acting with diff on the zero forms x, y, and z, which are the coordinate functions. Now, here is how we can define a type 2 differential form. You see here that we use the coordinate function to express it in terms of its coordinates in this coordinate system. Now, if we evaluate the cell, it's more legible. And you see that the first term is the dx dy term that is multiplied by minus 1 over x squared plus y squared. And then the second term is a dz dx term that is multiplied by the function x squared plus y squared. So let's do something with it. Let's multiply this form by dz. So this will give us a 3 form on the three-dimensional manifold. And you notice here that we obtain a term that should vanish. So dz multiplies the dz dx term and gives a dz dx dz term. But you know that because of the antisymmetry of the wedge product, this should be equal to 0. But this is not what we obtain. If we want to have this rule applied on this expression, we have to use the function simplification. The function simplification is a very important function in the xAct ecosystem. It's used many times, and what it does, it is applying to canonical, like we have already done, and simplify rules until the expression is simplified as much as possible. So then you see this term vanishes, and we obtain something that is proportional to dx dy dz as we expect. Here is another expression that computes the exterior derivative of omega 2. Omega 2 is a 2 form, then its derivative is a 3 form, and of course it is proportional to dx dy dz. The components can be abstract symbols, and we want those abstract symbols to be scalars. So these have to be declared and treated as such by the exterior package. So let's say that we want to use psi x, psi y, and psi z as symbols that will be put in the expressions that give the components of some form. So we declare those symbols to be scalar functions. So this expression here means to apply def scalar function on each element of the list psi x, psi y, and psi z. So this is the same as writing a list where we write def scalar function of psi x, comma, def scalar function of psi y, etc., etc. The second line here instructs the exterior package to print those symbols in a way that we prefer, so that we can read the expressions more easily. So the symbol psi x will be printed as psi with subscript x, psi y, psi with subscript y, and psi z with psi subscript z. So after evaluating this cell, psi x and psi y and psi z can be used as scalars in expressions involving differential forms. So here is an expression that defines a 2 form using psi x, psi y, and psi z. You see that psi x, psi y, and psi z are the scalars multiplying dy dz, dz dx, and dx dy. It's easier to read by looking at the output. So you have psi x dy dz, psi y dz dx, psi z dx dy, and this is done in a cyclic way. We know that the exterior derivative of this form is related to the divergence of a vector with components psi x, psi y, and psi z. Let's look at this and verify. So we compute the derivative of psi, simplified, and indeed you see that we have the 3 form, dx dy dz, multiplied by dz, the derivative of psi z with respect to its third argument, which is the derivative with respect to z, dy with the derivative with respect to its second argument, which is the derivative with respect to y, and the derivative of psi x with respect to x. And that is nothing but the divergence of psi. Let's now use those colors to define a 1 form that its dx, dy, and dz scalars multiplying it, its components in this chart are psi x, psi y, and psi z respectively. So you see this form here. It is a 1 form. And we have already shown in previous videos that the derivative of this 1 form is related to the curl of the vector with components psi x, psi y, and psi z. So let's verify this. that is the derivative of phi, simplifying, and you can check that the components of this 2 form are the components of the curl of psi. Now let's see how to compute a change of coordinates. We have defined Cartesian coordinates. Let's try to write down expressions that involve spherical coordinates. For that, we have to define a new chart. The old chart, called Cartesian, of course still remains. We can define many charts on the same manifold. So def chart now defines a new chart. It gives it the name spherical. It refers to the manifold M3, which we have already defined. Indices take values 1, 2, 3, and the coordinate functions are now called r, theta, and phi. So we evaluate this cell. You see everything that is done under the hood. I advise you to read those messages. And now let's define the rule of the coordinate change. So we define a rule, we call it Cartesian to spherical, and it transforms the functions x, y, and z to r, theta, and phi. And we use the well-known relations that relate Cartesian and spherical coordinates. So this is a list of rules that will be applied to any expression that we write. So let's consider the form omega 2 again, as before. But now let's make a change of coordinates. So we take omega 2 as it has been defined in the previous cell, and we apply the rule Cartesian to spherical. This will substitute the functions x, y, and z by their what is defined here in the substitution rule. So x will be replaced by r sine theta cos phi, y with r sin theta sin phi, etc. Furthermore, this will be also replaced within the differential function, and differentiations will occur. So in the end, we will have the omega 2 form with its coordinates in spherical coordinates. So you see here we have an expression that is a linear combination of dr d theta, dr d phi, and d theta d phi. Now this is the volume form in Cartesian coordinates, dx dy dz, but we can write that in spherical coordinates by making a coordinate change, and we obtain the familiar equation giving us the Levi-Civita tensor in spherical coordinates, which is dr d theta d phi multiplied by r squared sin theta. R squared sin theta is nothing but the determinant of the metric. Here we define a 3-form omega, which is equal to epsilon, and let's see how to integrate this form. So to integrate this form, we know from how integration is performed for n forms in an n-dimensional manifold, in our case n equals equal to 3. All we have to do is to write the n form in an expression involving the coordinate basis, and then perform an ordinary integration of the function that multiplies this n form with respect to r, theta, and phi. So in order to perform this integration, we have to select the function r squared sin theta and integrate it. So let's see how to do that and play with the heads of expressions. So let's look how omega looks as an expression in Mathematica, inside, under the hood. So you see that there is a times, then you see r squared is an expression involving the head power of r and 2, and we have sine, theta is the character theta, and then you see all the wedge products have a wedge as a head. If you apply the function head on omega, you see here times. This is its main head. But now, what you can do is to take this expression that has all those heads inside to do these computations. You see, it's kind of complicated. All expressions here have different heads. You have the times head, the power head, the sine head, the wedge, etc., etc. So here we use something like a regular expression, which is the underscore character in Mathematica, and we say apply this substitution rule where everything that has a head to be wedge should be replaced by 1. So everything here that is within the wedge expression will be replaced by 1, and that will leave us just with the function here, r squared sin theta. So you see, this is the function which we can now integrate using the ordinary integrate function of Mathematica. So we have this expression here, and we ask Mathematica to integrate it with respect to theta, going from 0 to pi, and phi going from 0 to 2 pi. And that will give us the area of a sphere of whose radius is equal to r. So let's move now and study something in higher dimensions. So let's go to a 4-dimensional manifold whose geometry is given by the famous Schwarzschild geometry, describing a static black hole with no angular momentum and no charge. So we will learn more about that later, but in our case all we need to know is that this metric is given by this expression in a coordinate system that has t, r, theta and phi as its coordinate functions. Note that the volume element here is given by the determinant of this metric. The metric is diagonal, so its determinant is obtained by simply multiplying all those functions in front of the two forms, dt squared, dr squared, d theta squared, etc. And its square root is obtained by taking its absolute value, of course. And after we have the square root of minus the determinant of g, we can define the Levi-Civita tensor to be the expression of this determinant in the coordinates dr theta phi multiplied by the 4-form dr d theta, dt dr d theta and d phi. So now we want to start a new exterior session. So we want to erase all symbols that have been defined before, so we use the function quit. The function quit will not quit your notebook, don't worry, but it will quit the kernel. So all the definitions that we have already done before will be erased. So we evaluate this cell, and of course now that now we have to reload the xTerior package to make it available to the kernel. Everything is restarted from the beginning. We do that quite often when we work with xAct. So now let's define a manifold which is 4-dimensional, M4, and we define two charts. One chart has coordinate functions dr, theta, and phi, and the other has u, v, theta, and phi. The first we will call it the dr, theta, phi chart, and the other will be called the Kruskal chart after the name of this coordinate system, whose usefulness we will study later in more detail. Now there is a mass here in the expression for the metric, which we wanted to be treated as a constant symbol. So we have to declare m to be a constant. So you see a lot of messages here. Again, as I have already stressed, it is instructive to read those messages. So let's define the Levi-Civita tensor to be a 4 form. So we give it the name epsilon here. It is defined on the manifold M4. It is a 4 form given by the value of this third argument, and we want it to be printed as epsilon. So we define its value here. Its value here, as we have already mentioned here, is given by r squared sin theta, which is the determinant of the metric, times dt, dr, d theta, and d phi. And indeed, this is what we get. Now let's make a coordinate transformation. So the coordinate transformation from the dr, theta, phi coordinates to the Kruskal coordinates is given by those expressions, provided that r is greater than 2m. So, as before, we define this change of coordinates as a rule that takes the u and v coordinate function and transforms them to expressions involving r and t. So we evaluate the cell and we obtain this. So now we can write expressions here, and what they compute is du. Of course, du in the Kruskal coordinate system is simply du, but if we want to see how it is related to the one forms in the dr, theta, phi coordinate system, then we have to apply this coordinate change rule, and we simplify this expression with the simplification function. So you see here the result. Try to do this calculation by hand. It's not so hard. It's kind of tedious, but it is not hard. It's straightforward. So let's compute now the volume element in Kruskal coordinates. Now in Kruskal coordinates, the expression of the metric is like this in these coordinates. So we have a minus dv square and plus du square term, but this is multiplied by this function involving r, and then the rest of the metric is the ordinary metric on in spherical coordinates. So that describes a two-dimensional sphere for fixed r. Now be careful, this r here is an implicit function of u and v, which we do not write down explicitly because you cannot write it in closed form. So the determinant here is computed by the product of those functions. The metric here is again in a diagonal form. So you see that the determinant of the metric is given by this function here. So let's define the volume form. The square root of g is 32 m cubed, blah blah blah, doing some elementary computations here. It's given by this expression. And then we define epsilon to be given by the square root of g in these coordinates times du, dv, d theta, d phi. So this is the value of epsilon in the classical coordinates. Now, if we do a coordinate transformation from classical to tr theta phi, then we obtain back the expression that we had before. Now you may have found the notation of entering expressions with the exterior derivative too cumbersome. So instead of using diff here, we can define a simpler symbol by defining, for example, the small letter d to be diff. Then we can write expressions that are less complicated. So you see now when d is applied on epsilon, it is the same as diff applied on epsilon. So we obtain the same expressions as before. And here is another example of a simplified So here we write the volume element in classical coordinates, square root of g, and now the du, dv, d theta, and d phi are written in easier to use notation. So let's play a little bit more with simplifying notation. First, we quit the kernel again to start anew. Then we load xTerior again. And now we define the four-dimensional manifold using slightly different notation. So again, I define the four-dimensional manifold M4 with indices mini alpha, beta, gamma, delta, alpha, gamma, sorry. And then I change a little bit notation for the coordinate function. So instead of using small letters, I use capital letters for all of them. You will soon see why I do that. So again, I have tr theta phi, but now the symbols are capitalized, and here I have u v theta phi with all symbols capitalized. Mathematica doesn't care about that, so xAct is making the appropriate definitions and declarations. But now we create a dictionary between the names of the coordinate functions and symbols that we consider easier to use as. So for the name of every coordinate system, I take names that are, do not use square brackets, and they are the small letter version of their names. So t is equal to t capital, and dt is the differential of t. So you see now with those definitions, I can use tr theta phi and actually mean the zero forms, tr theta phi representing the coordinate functions, and dt, dr, d theta, d phi to actually mean the differentials. Also, I use print as for t capital now to be printed with a small letter t. If I don't do that, I will see the original names of the coordinate functions. So you see here a non-trivial use of print as compared to what we have done before, where we change the name of the symbol to something else that we find more convenient. So we do that for all names, tr theta phi, u and v. Now, for example, we can write the coordinate transformation in a simpler way, with less typing, less prone to errors, and easier to read. So we do that. You see that it is printed correctly. So let's define again the for form epsilon. And now it is given by du, dv, d theta, and d phi, where you see now that I write the shorthand notation for the differentials of the coordinate functions. Also see that in the square root of g, I don't have to put the square brackets as before for r and theta. It would have been an error in the way that we have used it before. Remember that here in the rule defining the coordinate transformation, we have to use the square brackets here to be correct. But now, after applying this dictionary, we don't have to anymore. But also be careful with this notation, because you have to know what you're doing so that you don't obtain erroneous results. So this is a challenge to try it and try to understand what it's doing. But doing it as you should, you may avoid subtle errors in more complicated calculations. So use it at your own risk. So look what happens if I apply the coordinate transformation on the Levi-Civita tensor. I obtain the same result. You see here dr, dt, d theta, d phi. Here are other expressions. du, dv, etc., and how they transform. This is the result. And as a check that we're doing things correctly, let's take the d of this and see whether we obtain the same result as above. And indeed we do.